The purpose of this lecture is to more carefully study what we mean by x squared if x is a random variable, or more generally what we mean by a function of a random variable. So let's start with a simple example. I have a sample space which consists of the possible outcome A, B, and C. Let's allow all possible events to be our events. We have 3 possible outcomes, so there are 8 possible events. We'll do the simplest probability measure. We assume that each outcome is equally likely. Finally, I have a random variable x, which you remember is a function from S to R. So it needs to map each outcome into a real number. And let's say it does it like this. A to 1, B to 2, and C to 3. The range of x contains 3 numbers, 1, 2, and 3. So it's clearly a discrete random variable. And if the possible outcomes are equally likely, then it's easy to see that the probability mass function is given by 1/3 for x equal to 1. There is a 1/3 probability that we will end up with a 1, and that happens exactly when the experiment picks A. 1/3 x equal to 2, 1/3 x equal to 3, and 0 for all other x. Moving on to the important question then is, what then is x squared? Well, the basic answer is that it is a new random variable. It's a new random variable, and we're going to call that y, capital Y, to remind ourselves that it's a random variable, and a different symbol because it's not the same random variable as x. So exactly what random variable is y? Well, to describe a random variable, we have to describe exactly how it maps the possible outcome. That is what the random variable is. So we have to describe y of A, y of B, y of C. Once we have done that, we have our random variable. It's a simple mapping from S to R. The way we define it is that y of A will be equal to whatever x of A is squared. Squared because y is x squared. So this will be equal to 1 squared because x of A is 1. Y of B will be equal to 2 squared, which is 4. And y of C will be equal to 3 squared, which is 9. This is our new random variable. So you can see the principle is pretty straightforward. Just go through every possible outcome of x, 1, 2, and 3. Plug each outcome into a function, g of x, which is x squared, and that will give you the possible outcome of y. We can also derive the probability mass function of y. So let's write that here. Since I have now 2 random variables, it's common to put the name of the random variable as a subscript of f, because these are now different functions. So fx of x is the PMF of x, while fy of y is the PMF of y. What's the range of y? Well, it's 1, 4, and 9. So let's put that here, 1, 4, and 9. What's the probability that y will take the value 1? Well, that happens exactly when x takes the value 1. And that again happens when the experiment ends up with A, so that must be 1/3 as well. Similarly, 1/3 probability that y will end up with 4, and 1/3 that y will end up with the 9. Now, the final thing I want you to note about this is that we actually don't need to know anything about the experiment, the probability measure, the sample space, and how x maps outcome to the real line in order to figure out the PMF of y. So all I really need is the PMF of x. If I'm given a PMF of a random variable x, which is this, without knowing anything about the experiment, about the sample space and so on. And I define y as x squared. Then I can, from that, derive the PMF of y without figuring out how y maps each individual outcome to a real number. X is equal to 1 with 1/3 probability. That must mean that y is equal to 1 with 1/3 probability. X is equal to 2 with 1/3 probability, so y must be equal to 4 with 1/3 probability, and so on. So let's have a look at this from a more general perspective, in order to understand that the function of a random variable is simply the composition of two functions. So here is the general picture. I have x, which is a random variable. That's a function from my sample space to R. So if this is my sample space, and let's put R as a blob in this case, the collection of real numbers, then x is simply a mapping from S to R. Let's put it like that. If omega is one outcome in my sample space, then x will map that into x of omega, which we typically denote by lowercase x. So this is the standard setup for a random variable. Now, if g is a new function, the domain of g is R and the codomain is R as well. Then, since the domain of g is the same as the codomain of x, I can make a composition of these two functions. So I can start with an omega, I can map that into lowercase x by the function x, and then I can plug this into my g function. So I can do the g function here, and that will then map into, again, the collection of real numbers, because that's the codomain of g. So this particular point, lowercase x, will be mapped to g of lowercase x. And we denote that by lowercase y. So this way I go from omega to lowercase x to lowercase y. The composition of both these functions will take me straight from omega to lowercase y. And this composition is then the random variable y. It will map the specific outcome omega into the lowercase y, which is exactly what we get if we do the double jump from omega to lowercase x and then to lowercase y. So y of omega is equal to lowercase y, and lowercase y is also x of omega, that's lowercase x, plugged into the function g. So this is also lowercase y. That is, the function y is simply the composition of g and x. And we can also write y of omega is this composition, g ball x of omega. The common notation here is that we write this as y is g of x, ignoring the argument omega. That's the common notation. But this thing here means precisely this thing here. The same argument as we had for the example applies to this general situation. I actually don't need to know anything about the sample space, the possible outcomes, exactly how x maps sample space and so on. All I need to know is the distribution of x. If I know the distribution of x, either because I know the CDF, or if x is a continuous random variable, I may know the probability density function. If x is a discrete random variable, I may know the probability mass function. Anyway, I know the distribution of x and I know exactly the function. So y is this function of x. With this information, I can figure out the distribution of y. If x is a discrete random variable, this is typically pretty straightforward and not difficult at all. Like in the example, we just go through all the possible outcome of x, map them through the g function to find all the possible outcome of y. However, if x is a continuous random variable with the probability density function, it is slightly more difficult to find the distribution of y, and that's a topic for another lecture.